Hey everyone, so today we're going to dive into a pretty cool secret that's hiding in something you probably have in your kitchen right now, sugar. We're going to see how a simple sugar solution can actually twist a beam of light, and more importantly, how we can measure that twist with some amazing precision. Let's get right into it.
So here's the big question, right? How on earth can dissolving some sugar in water give that solution this, well, almost magical ability to twist light? It's all thanks to a phenomenon called optical activity, and by the end of this, you'll know exactly how it works.
All right, here's our game plan for today. First, we'll uncover sugar's secret ability. Then, we'll get into the theory behind it all. We'll meet the key piece of equipment, the polarimeter, and then walk through the experiment step by step. After that, we'll crunch the numbers, and finally, I'll give you some essential tips for the lab. Okay, so what is this secret we're talking about? Well, it's a property called optical activity. It's this invisible characteristic that certain molecules, like sucrose, have that lets them interact with light in a very specific and very measurable way.
Here's the main idea. Think about normal light, from a lamp. Its waves are vibrating in every direction, just all over the place. A polarizer, well, it's like a gatekeeper. It only lets the light waves that are vibrating in one specific direction or plane get through. That's what we call polarized light. And when this super organized light passes through a sugar solution, the sugar molecules literally twist that plane of vibration. Our whole mission is to measure the exact angle of that twist.
Okay, that's pretty cool, right? But how do we actually turn this observation into a real, solid measurement? Well, that's where the theory comes in. We need to understand the why to really nail the experiment. So we're not just measuring any old rotation. We are laser focused on finding something called specific rotation. And you can really think of this as a unique fingerprint for a compound. It's a standard value that tells us how powerful that substance's light bending ability is, no matter how much of it we use or what size container it's in. Now, the actual twist you see in the lab, it's not a fixed number. It can change based on a few key things. You've got to consider the wavelength of the light you're using, the temperature of the room, the length of the tube the light has to travel through, and, of course, how concentrated your sugar solution is. To find that unique fingerprint, we have to factor all of these in. And this right here is the master formula that pulls everything together for us. It's how we calculate the specific rotation, that's the S value. We take the angle we actually measure in the lab, which is theta, and we relate it to the length of our tube, L, and the concentration of our solution, C. Okay, so how in the world do we actually measure something we can't even see? We're going to need a special tool for the job. Let's get introduced to our instrument of the day, the polarimeter. All right, let's just trace the path of the light beam through this thing. It kicks off at the light source, then bam, it hits that first polarizer, which lines up all the light waves nice and neat. Then it travels through our sample tube, where all the magic happens, all the twisting. And finally, it gets to the end, to another polarizer we can actually turn, called the analyzer. By turning that, we can figure out the exact angle of the twist. Okay, enough theory. Let's get our hands dirty, so to speak. We're going to walk through the actual step-by-step procedure for this experiment. Now, this is probably the most important part of the whole observation. When you peek through the eyepiece, you're going to see a circle of light that's split in two. Your job, and you have to be super careful here, is to rotate the analyzer until those two halves become perfectly equally bright. You want to go from that uneven look on the left to this perfectly uniform circle on the right. Getting that balance just right is everything. The actual process is super systematic. First, you've got to make your sugar solution, and you have to know the concentration precisely. Then, step 2 is all about getting a baseline. You fill the tube with plain old distilled water, find that equally bright point, and write down the angle. That's your starting line. After that, you swap the water for your sugar solution and find the equally bright point all over again. That's your new angle. Simple, right? The difference between those two numbers is the twist from the sugar itself. All right, we've got our data. Time to switch from lab mode to math mode and crunch these numbers.
So, to get the true angle of rotation from the sugar, that's our theta, you just subtract the water reading from the sugar reading. It's that simple. The water reading is just our 0 point, our baseline. We're just figuring out how much the sugar shifted things.
And look what's back, our master formula. We finally have our observed angle, theta. We already know the length of the tube, L, and the concentration we made, C. So all that's left is to plug and chug. Okay, let's run through a quick example to see how it works. Let's say we measured our angle, theta, to be 25.1 degrees. We know our tube length, L, is 2 decimeters, and our concentration, C, is 0.2 grams per cc. We just pop those values right into the formula. So it's 25.1 divided by 2 times 0.2.
And there we have it, a specific rotation of 62.75. And check out those units. They're super important because they show we've accounted for all the variables to get this one standard fundamental number for cane sugar.
Okay, before we wrap up, I want to go over some absolutely critical tips. Honestly, think of this as your cheat sheet for getting good results and for acing any questions your lab instructor throws at you. For the Viva.
Listen up, because these are the deal breakers. Your tube has to be sparkling clean. Seriously. And you've got to make sure there are no air bubbles in the path of the light. That little bubble will mess up everything. Your solution? Crystal clear, no dust. And when you're taking readings, always aim for that equally bright sweet spot. Oh, and don't forget to write down the temperature and what kind of light you're using. And last but not least, be nice to the equipment. Turn off that lamp when you're done.
So, what's the big takeaway from all this? Well, we started with a really curious idea, right? That sugar water can twist light. And we ended by putting a hard number on it, a precise measurement. We've basically quantified a fundamental property of a molecule. And you know what? That's what experimental physics is all about.
And that brings me to one last thought for you. Sugar is definitely not the only thing that does this. Tons of things are optically active. Essential oils, amino acids, even some plastics. So now that you know how to do this, what else could you test? What other secrets are just waiting out there to be measured?